Well, thank you so much for inviting me here. It's such a pleasure and honor. And it's been a fantastic conference. I mean, and the efforts of these two is, and, and Aled, I suppose, is just great. I don't know, when I was on my way here, I was just thinking, what can I say about it? Because there were so many great results. And I even started dabbling with an adjective historical, something that I would never, something I would normally never use. Yes, but someone still has to speak about some products as a major open problem. And since Yoji is gone, then it's one of us in the audience. So I'm happy to talk about it. I guess the acknowledgements being done, let's move on to the introduction. So this is a quote from 1983 paper by Erdos and Semiredi. I wish I could do a bit of Hungarian accent, but no. So we have a sequence of integers and consider the integers in the form terms of product. And it's tempting to conjecture that for every epsilon bigger than 0, there is a threshold n0, such that for every bigger n, there are more than n to the power 2 minus epsilon distinct integers of the form in this form. Then they say, moreover, we conjecture that the same thing holds for k-fold sums and k-fold or k-fold products. And further, they say, perhaps our conjectures remain true even if the A's are real or complex numbers. So I'll mostly speak about this case, which is still pretty wide open, and just maybe mention a few words about k-fold products, because at least now we know, well, I'll just say it for k-fold products now. For k-fold products now, from the work of recent breakthrough, the Martin conjecture by Green, what's the correct alphabetical order? Green Manners, no, Green, no, Gowers. Gowers, Green Manners, and Tau. That now we actually know that this thing grows if we take long enough. If we take long enough k, we will grow up to any size we want, up to any power of n. I mean, that is pretty slow.
Maybe you should mention Akshat's contribution to that.
Then, and the quantification of this is Akshat's contribution to this. So the best known results still come from the geometric methods, and these are kind of the tools I've listed. So one is this picture by Schoimosche back from 2008 that everybody knows, presumably, and then there are incidence theorems, and the incidence theorems are first and foremost the Semiredi-Trotta theorem, but the Semiredi-Trotta theorem, we know it's only in the real or complex plane, well, something of quite quaternions as well. And then in positive characteristic, there is the version of the incidence theorem is a theorem due to Sophie Stevens and Frank Deseo, and also there is this point plane theorem attributed to myself in 2014 or something like this. And the other component to get the state-of-the-art results is Skredov's method of high energies, which enables you kind of to boost your boost your estimates by using them several times. So these are the current world records. So that basically the best known sum product exponent is slightly bigger than 4/3, and the 4/3 is due to Schoimosche and Schoimosche sectors, what I call. Shall I draw them, or I mean, I'm sure that everybody knows what they are.
So 2 minus epsilon is known.
Well, for this episode.
Okay, so what is the conjecture to be?
Ah,
Oh, okay.
yes, for any epsilon. Right. So essentially, the best exponent we know is just 4/3 plus a little bit, and this little bit was quite a difficult sort of work by Kanyagin and Skredov in 2014-15. So they again came up with an idea how to strengthen a little bit Schleiermach's construction, and then I mean this is just the quantification of of what they've suggested. And so when I was preparing this, I didn't realize that all this works for complex numbers and even quaternions. But as a matter of fact, this is wrong. So this also holds for complex numbers and quaternions. So all this methodology works in that case as well. Over FP, so of course, I mean, people would look at this problem over FP, and it was started by in the paper of Burgan, Katz and Tau in 2003. And over FP, the problem is interesting when the set that you're dealing with is small enough relative to the characteristic, say less than root P. I mean, in some instances, with some methods, you need to work with slightly smaller sets like P to the 1/3. But so basically, you're talking about smaller sets. If the sets are big, things are much easier. And the best known exponent is 5/4. Yeah, so this is wrong. This should be 3/4. Sorry. There is a paper by Grosso saying that the finite field case behaves in about the same way as the complex case for extremely small sets like log size. Yes, so the 5/4 is the best known for finite fields, and this is basically this comes from using sort of this technology because Burgan, Katz and Tau in 2003 they only had a quantitative result, just saying that some product inequality holds. Right, so we understand the situation much better in asymptotic cases. So asymptotic cases, FSMP meaning few sums give many products, or FPMS, few products give many sums. So as far as few sums give many products, it's very easy. This is Schleiermach's inequality, which immediately tells you that if the number of sums is about the size of A, you get as many products as you wish. Unfortunately, we don't have a version of this for K-fold products, for longer products. The story with few products give many sums was much more involved and much more interesting. And the first result was the paper of Burgan and Chang in 2004. And this is the kind of estimate that the paper had, and the paper worked for integers only. So if you look at this, you see that what you have is that for every epsilon, the power of the multiplicative doubling constant would grow pretty badly, but nonetheless, this is a strong estimate, of course. And then this was, well, I say, demystified and reproved by in a work of Zhilizov and Palvolge in the late, so the paper came out in 2020, and there was another paper of Dima Zhilizov with Imre Ruja, George Shakan, and David Matolce, the son of Mate Matolce, who proved some lemma that they couldn't prove for them, who was, I think, not even an undergraduate then, or maybe in the beginning of his undergraduate. Yes, and so this result was reproved over the integers. And then it was reproven again in the 2023 June paper by what I called at the time the trio, Green, Manners, and Tao, in their first entropy paper. And then finally, when the trio became a quartet and when Gowers became part of it, they proved the weak PFR. And now actually we know a beautiful result which holds for complex numbers. So for complex numbers, now we know just this.
Misha, is it complexes or just reals?
I think I don't see any obstruction to make it complex because subspace theorem is for complex numbers.
I think weak PFR might just work for reals, but I don't know.
No, I mean, I think it's just, I mean, when I was thinking about it, I didn't see the difference between, but say, okay, maybe.
I think over the integers, we don't get anything stronger than Sheldraff. I think if you just a tiny modification to their argument would give the bound at the bottom for integers. I mean, they essentially state it. Jalashov states it in a lecture somewhere.
But I think once you have the weak PFR, I mean, if you have it for reals, why would you not have it for integers?
You do have it for integers, but they proved it for integers. So the result at the bottom is a result of that over the integers.
Ah. Okay, thank you. So, and in positive characteristic, we don't have anything like this. We have partial results only. Essentially, in positive characteristics, what we have is that if the product set is small, we can pretty much not say anything we would like to have about, well, we can easily say that the sum set is, if the product set is small, the sum set is bigger than a⁻². That's not difficult. We can, with a little bit more muscle, say that a⁻A is slightly better than a⁻². And we cannot say it about a+A. And on the few sums many products side, we don't have the full strength result either. We can say that if we have few sums, then the number of products is at least a⁸. Okay, so how do we go about? That's just very brief. So we use energies, of course. So this is additive energy, this is multiplicative energy, and having an upper bound on energy gives you a lower bound on the cardinality. So it's by standard Cauchy-Schwarz application. And one thing is that for bookkeeping, it's just good to notice that if you take an exponential sum with the frequencies and you said A, then the energy is just the fourth power of the L4 norm of the exponential sum. And usually the strategy of proving some product estimates would be bounding energy via the opposite sex. Sorry, set. So, for instance, Schleumoscher's paper was called bounding multiplicative energy via the product, via the sum set, and that was a bound. And in the few products, many sums case again. So this is what I thought was the correct formulation of the bound. So that if we have that the product set is small, then there exists a large subset of A such that we have almost an optimal bound for the energy. If that's possible. I mean, but then we pay the price we pay is this power of m. So again, I guess I should be cautious what I say about the BFR and the case of reals, but the way I understand it is that what follows from the state-of-the-art results is that we can prove that there exists a subset of A, which can be made any desirable proportion of A, such that essentially the maximum number of realization, any sum or difference in this set, is just bounded by goodness, just by this. So it's reasonable to ask, I guess, if the following is true. So we know that in the asymptotic cases, we have the energy bounds via the opposite set, which are as good as we want. So is that true in the whole range of cardinalities? Is that true that we can take, say, the sum set in the sum product conjecture and replace it by what Cauchy-Schwarz would have given us, and allow ourselves to move on from sets to subsets, because I mean, otherwise you would have easy counterexamples. What do you think? Is that correct statement or not? No, it's not. So the best you can expect here is the best exponent you can expect is 5/3, and that was an example provided by Balog and Woolley, and I guess it makes sense to show this example. So what you'll do is you take the size of A equals little n cubed, and the way you'll construct A is as follows. You'll say take an interval between 1 and n squared, and then you take a huge number p, say much bigger than a huge prime p, much bigger than n squared, and dilate it by p. Oh, let's call this set A0, and this is p A0, and then you take another dilate by c squared. And then finally, you'll take all the dilates p to the n, A0. And then it's, of course, easy to notice that that the product set is at most n to the 5th, because when you multiply, I mean, powers of p is in arithmetic progression. And on the other hand, the energy is at least the sum of energies of each arithmetic progression, which is n to the 6th times n, which is n to the 7th. And this is it. And even the little o is there because when you take the products of these things, you don't get everything either. So hence this this claim.
Misha, is that n to the 6 meant to be something else? Maybe and
No, the energy of each individual piece. So there are n squared elements in each individual piece. Wrong direction. So this is just same thing about the example. And yeah, so it's good to notice that if you take any positive subset, I mean, any positive density subset, nothing will change really. And I guess the rest of the talk I'll since I want to say something new about the sum product problem, the rest of the talk will be about this new result by myself with Brandon, Ilya, and Dima Zhelezov. And this is the theorem, so that's which is true for integers, that this is the inequality we get. And I guess I wish someone asked me a question about the formulation.
What are
Thank you. Yes, so the theorem holds only under condition that every integer in the set A has at most r prime factors, and the only r we can deal with is a small power of log A. We absolutely don't know what to do when the power would be just log A. This question was asked by Simiredi to Dima at some point. I need to say that it doesn't mean, of course, that the whole set is spanned by the same primes. No. So the primes and the decomposition of each integer can be different. If it was spanned by just the log A primes, we wouldn't have to do anything pretty much.
I'm a little bit confused by what little o sub r means. Does it actually mean little o sub epsilon?
Little o sub r. So these, I mean, these are factors which are smaller than any power of the size of A, and these factors depend on, I mean, so the error depends on R. But as long as R is sublogarithmic, I mean, is smaller than any power of log. So this is just a little O of 1, but just saying that this term becomes worse as R increases.
So again, does it actually mean little o sub epsilon?
Yes.
So only fixed epsilon?
Yes.
Oh, yes. I see. So maybe it's worth mentioning that we can modify this Balagouli example, and instead of this interval, just take an arithmetic progression of primes of length and squared, and take another huge prime P and dilate that arithmetic progression of primes. And in this case, in the Balagouli example, R will be equal to 2. And as a matter of fact, we understood how to prove this theorem once we were able to deal with the case R equals 2. So transition from R equals 2 to higher values of R wasn't so hard. There is an interesting corollary to it. So in the sum product literature, people are often people have often been looking at this quantity, which is, if geometrically, would be the number of set of scalar products within this number of dot products within the set A cross A. And presumably, of course, this quantity should be at least A squared, and it's not even clear if there should be any kind of epsilon there. However, we don't know this, but from the methodology of the proof, I mean, quite an interesting thing follows, that as a matter of fact, this quantity is bigger than A squared, as long as that this quantity can be, well, so how should I say that? Well, I mean, this is the inequality, right? But this quantity would be bigger than A squared unless M is as big as it gets or as small as it gets. So unless A has the maximum amount of multiplicative structure or the minimum amount of multiplicative structure. But of course, the constraint holds as well. And the proof has kind of three major components to it. And the first one is a structure theorem, which is kind of basic combinatorics, really. The second one is reasonably involved harmonic analysis. So we take advantage of sort of classical martingale maximal function inequalities going both ways. And at first we didn't realize that they just exist as a black box and we could essentially use a theorem from Wikipedia. Well, at least in one direction. So we were proving them themselves and then discovered that they're actually available. And the third one is a special case of Schmidt's subspace theorem. And with the subspace theorem that we stated, so actually there's a corollary of the subspace theorem, and Misha tells me that people who knows how to prove the subspace theorem actually distinguish between this corollary and the subspace theorem itself. But this is the statement. The statement that's, I mean, the strength of the statement is the one that is needed here. So if we just take a bunch of primes and use them as the generators for a subgroup, and then fix any collection of L complex numbers. L will be a parameter we're playing with. So back to the PFR, to the use of PFR, when I said that the subspace theorem is being used, L equals just 2. In this case, L is some parameter that we play with. And then if you take a linear combination of the elements of gamma of the group with some fixed coefficients and look at the number of solutions of this equation with no zero subsum, otherwise, of course, you can generate as many as you want, then this number of solutions is bounded. And what is important here is that this is basically the length, the power length times the rank of the subgroup. And the subspace theorem, so I think, so it's the first time I saw the subspace theorem mentioned in connection of the sum product type questions was in the 2002 paper by Meichu Chang. And then Schleumers and Schwartz in about 2000, maybe about 2012, something like this, wrote a paper on the use of the subspace theorem in geometric combinatorics, where they kind of tried to, I think, come up with questions where the subspace theorem would be useful. And since Jože is not here, to me, those questions kind of look a little bit far-fetched. So you kind of try and then there's no sort of genuine sort of difficult question that you could use it for, unless you put some strong restrictions to what you're asking, to the scope of the question. But here actually the subspace theorem comes in just so naturally and so nicely. And unfortunately, all these three parts I mean, none of these parts would work if we remove our assumption on the number of prime factors. And so these two parts sort of these two parts would allow us for the number of prime factors to be, yeah. So this one imposes the most stringent of all the three for the number of prime factors. Okay, so let me just say a word about the structure theorem. So just the usual regularization result. Let me just I guess explain what it says. So it just says that you can find a reasonably large subset of your set A and a bunch of primes, well, generating a group gamma, such that your set A looks like this. You have some base set B. This is the subgroup gamma. And for every member of the base set B, the size of the fiber gamma of B is about the same number, L. And moreover, I mean, the gamma is generated by a bunch of primes. So this fiber, I mean, this fiber consists of powers of these generators, of these primes generating the group. So you can think of the fiber as some kind of parallelepiped. And the sides of the parallelepiped are going to be some Lj. And the sides are also roughly the same. So proving something like this is very easy. Essentially, all you do is, oh yes, and most importantly, half of the pair, I mean 50% at least of the pairs in the base set B and B prime, they're co-prime. So in other words, when you multiply the elements of the base set with each other, you pretty much get the maximum number of products. And all the bad things that can happen to products come from multiplying the fibers. And then immediately that tells you, of course, that on the product set you lose L, because L is the size of the fiber. And the way you prove it is very easy. So you just ask a question. Well, is it true that, so you prove it iteratively. You say, is that true for with B equals A? Is it true that 50% of the elements of A are co-prime? Well, if yes, then you're done. If no, well, then there is a member of A which is not co-prime to many elements of A, and this member of A has a small number of prime factors. So you get a small number of candidates for a common prime. You take this best candidate and continue, and that, of course, hence the limitation on the number of primes that you can have. Right. So the fact that what we're doing is much easier than the general sum product problem is easily seen because the exponent 3/2, so we have 5/3, the exponent 3/2 comes cheaply. So it comes from the structure theorem plus a lemma by Mei-Chu Chang, which was kind of the basis for her 2003 annals paper on few products imply many sums, which was dramatically improved by 1 year later by Burgan and Chang. So this is a very simple lemma. So that's the content of the lemma. So suppose you have a set of integers and you have a prime P, and then you partition your set A into subsets AV, where by just the P valuation, by the maximum power of P multiplying the members of the set. And then when you look at the energy, when you look at the energy of A, you conclude that it's not possible that the p variations of all these four terms are different. I mean, two of them have to be the same. Therefore, since two of them have to be the same, well, let's just say that these are these two that have to be the same. The power of p multiplying these two guys is the same, and the power of p multiplying these two guys is anything that or greater. And so you have that the energy of A is bounded by this quantity, by the joint energies of the sum over variations of the joint energies. Then you apply Cauchy-Schwarz and cancel this out.
Symmetric.
So I put down symmetric because I didn't want to mess around with plus or minus signs. So just say yeah. You can iterate this lemma for more primes than just one prime. And once you've done the calculation and you evaluate the energy of A, you see that on the energy estimate, you win L. So the worst possible case, so the size of A prime is L times B. So the worst possible case would be L cubed, B cubed. But when you use this lemma, you win L, and then you lose L on the products, you win L on the energy, and so hence the 3/2 exponent.
Remind me what L was.
L was the size, L is the size of this fiber. So yeah, let's put it down. So the size of A prime is roughly L times the size of B. So A prime looks like a collection of fibers over this base set B. Elements of B are co-prime. So let's think that all pairs of elements of B are co-prime, and there is a fiber of the elements of this group gamma. I mean, for every base element. And the most of the work was this moving on from 3/2 to 5/3, and this is where the non-trivial, I mean, part and an external part of the proof comes from. So essentially, let me just. So this is our main proposition is strengthening Chang's lemma, and let me just show on the picture how this is strengthened. So if we look again at the same picture, and then we look at the energy. So we have 4 A's in the energy, and let's take 4 B's. Corresponding to these 4 A's, and this is the gamma axis. So Urgan and Chang, Chang's lemma says that. So this is the A space. Chang lemma says that B1 and B2 must have the same fiber term, whereas B3 and B4 can be anything. Well, say bigger. And the way we strengthen it is by saying that no, B3 and B4 also should have same valuation.
Valuation bigger, valuation one for both, and the difference could still pass.
Well, greater than or equal.
Like be smaller, or do just.
Oh no, this is just moving things around. That's why I said symmetric, that I can always sort of move things around and not distinguish between plus and minus signs. And once you have this, qualitatively, when you look at the energy of A prime, so now what you have is that the energy of A prime now looks as follows. It looks like G1 B1 minus G1 B2 equals G 3 B3 minus G3 B4. And so obviously you divide by G1. And look at what you have. So you just fix a pair of B1 and B2 and make it a constant. And this is a constant times, and this is just an element of the group. So you put down a constant times gamma, the whole gamma. And that equals B3 minus B4. And you count the number of solutions of this equation. And this is when the subspace theorem kicks in. And once you've done the bookkeeping, you see that yeah, so I guess answering Ben's question, these are the precise losses. So this is kind of what the little term, what little O of R is in terms of epsilon, yes. And well, when you do the bookkeeping, you see that now instead of winning L on the sum side, that gives you 3/2, you win L squared. And so you lost L and you won L squared, and your exponent is 5/3. Maybe as a digression now, I should say that if you go back to the Balagh-Woolley example, which also gives you the same exponent. If you go back to the Balagh-Woolley example, of course, you can just split your set onto two different subsets, A1 and A2, such that there will be no additive interaction between A1 and A2 at all, because A1 would be on one sort of space scale and A2 will be just on a much bigger space scale. Unfortunately, our methodology with martingales does not allow us to do anything like this. So we can only talk about the energy of the whole set. And I guess the next thing is to kind of point out why and how. All right, so let's just think about one common prime, because then adding more primes does require work, and yeah, it does require a work, and I certainly didn't know how to do this when we were doing this, but it's feasible and quite standard for people who have some experience in harmonic analysis. So this is the main proposition again, that the p-valuations of these two terms have to be equal, and the p-valuations of those two terms have to be equal. And one remark is that no subspace theorem is needed for that, because you can just do things by hand by writing everything in base P. But so this is kind of a sketch of the proof for rank 1, for one common prime. So what you do is you take the exponential sum with frequencies in your set and split this exponential sum into chunks by the p-valuation, by the maximum power of p multiplying the corresponding a's. And then what you know is that the energy is the fourth power of the L4 norm of the exponential sum. And you introduce the square function. So for harmonic analysts, the concept of a square function is very familiar. And so this is like a Littlewood-Paley kind of, I guess Littlewood and Paley introduced it. So this is, you just Yeah, you just square, I mean, you take each chunk, I mean, square it and sum over the chunks and then just do the powers, have the powers match. And a good thing to notice at this point is that since you square here, and this is essentially how you can add more primes, you can observe that you can multiply each chunk by the phase by a complex number with modulus 1, and the square function will be the same. In particular, you can start throwing randomly plus minus ones at each chunk of your exponential sum, and the square function will be the same. And we proved this ourselves, but then we found it. The paper, there was a paper from 1970 by Burkholder and Gandhi, which was called a martingale commonly used in harmonic analysis. And it had a theorem that we could have just used, taken as a black box. And that was theorem 1 in that paper. So the theorem essentially says that for any q bigger than 1, any the LQ norm of f itself and the square function differ only by a constant factor. And this is true from above and from below. And this is also true for this is also true for the maximum function. So the maximum function is obtained as follows. You take your exponential sum, you truncate it, you throw away terms with p-valuations less than v. So you get this f greater than or equal than v. And the maximum function is just the supremum of all the maximum of these. And the way to prove this theorem is to look at the maximum function and prove the maximum function inequality. And this is how you prove it one way, and then proving, I mean, for one common prime, we didn't even need the other direction, but the other direction is easiest, follows by duality. All right. So why a martingale? That is very easy. So the whole exponential sum is a function on the circle. So it's a 2-pi periodic. Suppose now you only leave the frequencies which are proportional to p, to the prime. Well, then it's no longer a 2-pi periodic function. It's a function periodic on, the period now becomes 2-pi over p, and so on. So essentially, truncating the sum, so throwing away frequencies with p-valuations up to p to the v simply means averaging this function on a polygon with p to the v vertices. Averaging means martingales. And so, in other words, it's easy to show that this is, well, an inverse martingale. So this is how it goes. So f is the most complex, of course, as it is, and the truncations, the further you truncate, the easier objects they are. And once you have it, then you can go on Wikipedia and just take the martingale maximum function theorem, and then we wouldn't even need this paper for the case of one common prime yeah. And then once you have it, your upper bound is Cauchy-Schwarz. To add more primes, we still had to do some work. So we had to throw in some randomization. So as I said, the square function is invariant with respect to multiplying each piece, each chunk AV by a phase. Essentially, our enemy was that if this is our equation, A1 minus A2 equals A3 minus A4, and okay, we take the first generator of the first common prime, and we conclude that the p-valuations of these two guys have to be equal, and the p-valuations of those two guys have to be equal. But then we fetch another prime, and what if the q valuations of these two are equal, and the q valuations of those two are equal, and then we wouldn't be able to deal with this case. But fortunately, this trickery of throwing in these random sort of plus minus ones, and using both the direct and inverse inequality enables you to get away with and end up with. I think that's probably it about the proof. So what I'd like to think is, so basically, when we've proven this, and I started thinking, well, the sum product problem is about integers. So maybe it makes sense to go back to the original formulation and try to really prove the sum product theorem for integers. Then, unfortunately, the PFR kicks in, and then actually, which is purely combinatorial, and then they have it for reals. I mean, at least the asymptotic case, but they need the subspace theorem. So that is, again, so where does it belong, the sum product problem, in some sense? I think it's still below. I think we should think more about integers. And since there are so many talented and hardworking people in this audience, maybe it's time to replace like old timers like myself and actually prove at least, solve this problem in some setting. Yeah, I guess I'll stop here, and hopefully there are questions.